Thanks for the introduction, and thanks to the organizer for the kind invitation. It was a great conference. So I'd like to talk about generalized permutahedra and optimal auctions. So this is about a specific class of convex polytopes and an application to economic theory. And I should point out that this is joint work with Max Klimm, my colleague at TU Berlin, and Sylvain Spitz, who is here, who's a joint PhD student of Max and myself. All right, so that's what we will do. We will talk about deterministic auctions. So auctions are procedures to help people to make a lot of money out of selling stuff. And I will explain the specific setup that we will study here. And the goal, as I already alluded to, will be revenue maximization. And the most important player in this talk is a specific kind of auction, which is called straitjacket auction. And this is a name which came from a recent paper of Giannakopoulos and Koutsoupias, so the same Koutsoupias who was just mentioned before. And so this is the, if you will, the economic parts of the whole story. And then our main result is about the specific optimality result there. And this is driven by understanding the special class of polytopes, which have been called symbodies, also by Giannakopoulos and Koutsoupias. And one of our results is it's not so difficult to see that these are generalized permutahedra. But so the important thing is this allows for a very rich theory to be applied. And in particular, we are interested in computing volumes of these things. And then in the end, I will talk about specifically computing the prices. So these auctions are defined by prices. And I will sweep a lot of the details under the rug, but typically these auctions are defined in an indirect way. And then it is sometimes not obvious to see that the auctions with such properties actually exist. And so in this sense, this computation that I will show you goes beyond just showing that we can do sufficiently many interesting examples, but actually also establishing the existence of some of these things. All right. So, as I said, deterministic auctions is about selling stuff. And, And there are very, very many scenarios studied in economics. And our scenario looks very, very innocent because it is easy in the sense that we only have one person who wants to buy stuff and only one person who wants to sell stuff. And the only non-trivial contribution, if you will, is the fact that there's more than one item to be sold. So there are n items throughout the entire talk. N will always be the number of items. And then price schedule in our setting. And so this will always be deterministic as far as our results are concerned, but I will talk a little bit about non-deterministic in a minute. So in the deterministic setting, a price schedule is just an assignment of all the possible selections of items to be sold. So such a selection is always usually called a bundle. So for each bundle to pick a price. I mean, and this is the price schedule. And in the non-deterministic setting, instead of having a fixed price for a bundle, you have a lottery. So the buyer pays some amount of money in order to obtain the probability to receive certain items with certain probabilities. In the deterministic case, that particular probability is removed. I should point out, so an important technical assumption, which obviously makes sense, is that if the buyer doesn't get anything, he doesn't need to pay. Now, what does the buyer look like in mathematical terms? So the buyer has an opinion about each individual item. So there are these n items, and there's a specific value, and we normalize everything between 0 and 1. So a specific value that the buyer assigns to each of these items between 0 and 1. And that particular information is hidden from the seller. Otherwise, things would be boring. And but so the seller needs to work with something, and this is the fundamental assumption that we will always make here, so that these values are drawn uniformly at random. All right, so that's the assumption, and then the utility of the buyer is computed as follows. So this depends on these values, obviously. And then you maximize the sum of the things, so the total usefulness, if you, so the sum of the valuation. So the valuation is assumed to be additive. And you subtract what you need to pay in order to get a specific bundle. And then you maximize over all possible bundles. And so if you look at that, so this is in this, so this is a connection to tropical geometry, which is appropriate for this workshop, I think. It is so this thing is a max tropical polynomial. So this entire expression, and here in fact you see a square free tropical monomial. So it's a sum of variables. So tropical sum is this corresponds to the usual multiplication, and the coefficients are the negative prices. Okay, and you maximize over this, and so that's the evaluation of a max tropical polynomial of degree n, number of items. And the most important fact about these things is that such evaluation functions are always piecewise linear and convex. And I will come back to this in a minute. But before I do this, I need to explain what our actual goal is. So the goal is the perspective of the seller. So we already explained how the mathematical model for the buyer is assumed, and now we want to pick prices for the seller such that the seller maximizes their revenue. And so I always say revenue, and it always expected revenue with respect to the uniform distribution among all the possible values for the seller, for the buyer. So that's this thing. I said a word about non-deterministic scenarios, and in that non-deterministic scenario, so there are some standard assumptions. I just spell them out here for completeness, but I won't discuss them much. They are kind of automatic in our deterministic setting. But I want to, so the context is, so in this context, there's one fundamental theorem which won the Nobel Memorial Prize for economics. And this is due to Meyerson. It's a famous result in this area. And this concerns the case of a single item. So this is kind of, this is really the first case. So one buyer, one seller, and only one item. But so Meyerson considers the non-deterministic setting. And in the non-deterministic setting, it turns out that the best that the seller can do is to decide in favor of a deterministic auction, so really to decide for prices beforehand, and to pick for the single item the price 1/2 in this normalized setting. And this maximizes the revenue, the expected revenue of the seller. So this is Meyerson's result. That's the context. All right, so is there a question concerning our setup? All right, so interrupt me anytime. So now there's one important condition which adds interesting geometry, which was also mentioned in Cynthia Van Zandt's talk, for instance. So it's a submodular condition. And the price schedule is called submodular if that particular inequality holds for all choices of bundles I and j. So there are various ways in the economics literature to motivate this condition. And so in particular, so one way would be, well, so it's a natural condition for the seller to assume, because if this was not be satisfied, then the buyer could first, so suppose the buyer is interested in bundles I union j, right? And so if that inequality would not be satisfied, then the buyer could first buy all the items in j, and then all the items in I, and then all the items in j, and then sell the stuff in the intersection, and in order to make to strike a bargain. And So at least this argument works for iterated auctions of the same kind. And then this is obviously not in the interest of the seller. And so therefore it is useful to assume submodularity. That's one way of motivating this, this condition. This will appear. Okay, and now let's go back to our tropical setting and combine this with this submodularity. So what does it look like? So that's the situation for two items now. So everything happens in the unit square that you see here in white. And each point in the unit square is a pair of values for the two items for the buyer. And so that kind of information which is hidden from the seller. And now suppose we decided for the price for our item, for our first item. So that's the price P sub 1. And then that's the price P sub 2 for the second item. And then we have the combined price P sub 1, 2 for both items together. And we assumed so no items don't cost anything. Then what you see here is a subdivision of the unit square into 4 regions, which mark those value pairs for the seller, which maximize the particular usefulness at a specific bundle, right? So this means if the prices are chosen like this, then and if the utility of the seller lies, for instance, here, then she doesn't want to buy anything. Or if the values lie here, so then she wants to buy both, and similarly for all the other things. So you can imagine how this works in the general case. And the submodularity here occurs because this skew segment here cuts off the corner, the upper right corner of this rectangular that you can imagine here. Now, what is the tropical geometry? So this blue thing is now the tropical hypersurface, which was defined by this tropical polynomial. So these regions are the regions of linearity. And if you didn't see this tropical hypersurface business before, so this is exactly that part of the unit square where the buyer is indifferent with respect to at least 2 bundles, right? So this is, so here on this point, if the value lies here, so then the buyer doesn't care if she doesn't get anything or if she buys only item 2. Right, and similarly for the other things. And I will come back to this picture a little bit later. So that's the situation if the prices are known. Okay. And so how is the revenue computed? So this is also visible in this picture. The revenue is now a sum over all the possible prices for each individual bundle multiplied by the volume, the n-dimensional volume of the corresponding region, the region where that bundle is sold. And so where does this volume come from? Well, this is our uniform distribution assumption. All right. So this is now the expected revenue for the seller. So, and the important thing here is these individual pieces are convex polytopes, and we are interested in their volumes. And there needs to be, so for the optimal prices, some kind of balancing needs to happen here. And one more word about this situation, you can imagine if the prices just move by a little, well, then these shapes also move by a little, but all the blue stuff is just moved in normal direction. So meaning, so everything stays in parallel. Right, so that is the first approximation to the geometric situation. Now we need to do a little bit more concerning the details, and I want to get more precise. For the purpose of conciseness, I'm focusing on the special case where the prices only depend on the size of the bundle. So not on the individual combination of items, but just how many items are in a bundle. So that's the symmetric setting. Most of our results generalize to the non-symmetric setting, but require more words to be spelled out. And so in this scenario, Giannakopoulos and Koutsoupias developed a specific kind of auction, which they called the straitjacket auction. And so they used a primal dual approach, which is based on an idea of Rocher from 1985. And they showed that this particular auction is optimal for at most 6 items, even in the non-deterministic case. And they couldn't say anything about 7 or more items. And it is important that here to understand, I already said this in the beginning, so this particular auction is given in an indirect way by kind of a primal dual constraint condition, which just happened to match up for up to 6 items. And so this establishes also the existence of these auctions only for up to 6 items. From their work, it is not obvious how this would work for 7 items. And our result now is a solution to explain how this auction should be defined for arbitrarily many items. And we can show that this is optimal among all deterministic, submodular, and symmetric auctions. Well, with a little bit of a technical overhead. So there is some technical stuff that I will go into later. So some bad cases could happen. I don't believe this can actually happen, but we cannot exclude this with our current technology. And what's the new idea? Well, the idea is, as I said, so if you go back to this previous picture, right? So this one here, the idea is the revenue, if you're in this situation, and if you change the prices very, very slightly, then in a neighborhood, so the revenue differentially depends on the prices, right? So, and then if you want to optimize, then you want to look into a situation where all the partial derivatives of your differentiable function vanish, right? So this is like looking for critical points of this function. That's the idea. And if you're able to characterize this, then you should be able to find your optimum among all the critical points of this function. That's the idea. The sad truth is it's more complicated than that. And so the very idea goes back to Manelli and Vincent, but we needed to extend that idea because for the auctions that we're considering here, you cannot ignore degenerate situations. So it is not enough to just look at this differentiable scenario, because the optimum can be attained at the boundary, and does happen for many items. That's the main technical obstacle for this problem. All right. So, so one of the things that I need to do a little bit later, I have a few minutes left, is how this auction is actually defined. But let me postpone this, because before I do this, I want to talk about the specific convex polytopes that occur as regions in the picture before. And so they were called symbodies by Giannakopoulos and Koutsoupias. I'll explain the name. And so you have n parameters. Again, we are in this n item situation, and we still want to talk about prices later. So later the prices will be the sum of these parameters, and we are in the symmetric setting. That's why we only have one price per number of items in some bundle. Okay, but for now it's just about polytopes. And lambda of these parameters is a polytope which is defined, which sits in the unit cube. And so this is just the sum and the constraint. I have, oh yes, here's something missing. So it's not only one constraint, it's 2 to the n constraints, 1 for each subset of n. And capital I is a possible bundle. I sum over the xj's, and if this is below the price of the size of the bundle, so then the point x lies in this symbody. This is how it is defined. And here are pictures. And so the left red guy, so this is the situation for 2 items, depending on alpha 1 and alpha 2. Alpha 1 is larger than alpha 2. And so this is its big sister. So it is for 3 items. And so you can see that this is how this goes. So here you always have the full symmetric group of degree n operating. And essentially to construct this polytope, it suffices to know one point. So like this point alpha 2, alpha 1 in the left picture. And then you let the group operate and extend to the, and then you take everything below. So in the domination order. And so here on the right-hand picture, it's a little bit better to see. So if you pick V to be alpha 1, alpha 2, and alpha 3, you let the group operate, you get this hexagon, and then you take everything below in the unit cube, and then you get this sim body. And the name just comes from these SIM cards in our mobile phones, which is very appropriate in Bonn, because this is where the biggest provider of mobile phone communication in Germany resides. All right, so these are SIM bodies. And and here again, you see the picture that you saw before with this tropical hypersurface and these regions. But now I'm restricting to the symmetric setting, which means everything is symmetric with respect to the diagonal. And in particular, the volume of D1 and the volume of D1 here is the same. And that's why I'm giving it the same name. So, so here on the lower left, you see the D0. So this is the region where nothing is sold. And so the volume of this guy is the thing that will be of interest in a minute. But so first of all, so this D0 is the thing that this is exactly one of these SIM bodies. And also in the generic setting, knowing D0 is enough to reconstruct the entire tropical hypersurface, just by symmetry and by, because this has sufficiently many facets. All right. All right. So this is this thing. And now what about volume? Well, in the symmetric setting, here's again our goal. We want to maximize the revenue. And now, so this is the same formula as before, but I have the simplification, which comes from restricting to symmetric prices. Therefore, I need to count how often a price occurs, or how many bundles I have with the same price, since everything just depends on the cardinality. So this is this binomial coefficient and this volume. Now, this is, again, already occurs by Giannakopoulos and Koutsoupias, and they gave an integration formula. The interesting thing is there is many other formulae, and you can play with them, and all of them are kind of useful. And our favorite one is an algorithm of Jim Lawrence from 1991. That's a general algorithm for computing volumes of rational polytopes. And in our case, it is particularly nice because the polytopes are so nice. I will, this is on my next slide, what it means. So in particular, these are rational polytopes which have a smooth normal fan in the sense of toric geometry. So smooth normal fan in terms of optimization. So this is essentially the totally dual integrality condition of combinatorial optimization. And so now, I also wanted to make a connection to linear programming. Lawrence algorithm for computing the volume can be seen as a version of parametric linear programming of sorts. And so this works particularly well on these things. So there is a connection to algorithms for linear programming, and this is hidden here in this work of Jim Lawrence. There are also totally different kinds of formulae for computing the volume. For instance, there's one which goes through counting certain bipartite graphs, but that's for another day. But I will explain to you now where this actually comes from. So this comes from this main structural fact that we observed for these sim bodies. So these are generalized permutahedra. Let me first say the definition without writing them down, and then let's say a word about the history of the subject. So generalized permutahedra can be defined in numerous ways. One way of saying this, so a rational polytope is a generalized permutahedron if all its edges kind of point into the right direction. So what does it mean? So if all edges are parallel to differences of standard basis vectors, EI minus EJ. So this is, if this is true for all edges of the polytopes, simultaneously, then this is a generalized permutahedra. One super important case of generalized permutahedra, so they occurred several times during this week, are matroid basis polytopes. So you have a matroid and you just take the indicator vectors of the bases and take their convex hull. So then it's a theorem that so it's a consequence of the basis exchange theorem of matroids, that the standard basis vector differences are exactly the edge directions of these matroid-based polytopes. So this is known for a long time. So for instance, this was already known to Jack Edmonds, who had a seminal paper on these things. And in that paper, he also generalized the notion of matroids and matroid polytopes to polymatroids. And in a way, generalized permutahedra are just polymatroids in disguise, so in a different language. So the history continues. I mean, I'm going through a large body of work very, very swiftly. So it's important to mention the contributions of the Japanese school of optimization. Sorry. I had a bit of the cold at the beginning of the week, so my voice is a little bit dry. So Fujishige had a textbook, so this is only the textbook reference, which comprises a lot of prior work, of course, on optimizing submodular functions. This belongs to this field, and a little bit later, Morota, so generalized it into more geometric language to discrete convex analysis. And all of this can be understood at studying and generalizing and analyzing polymatroids. And in 2009, there's this paper of Postnikov where this name generalized permutahedron shows up for the first time. And so in a way, so this is still studying the same objects that already occur in previous work by Edmonds, Fujishige, Morota, and others. And but the specific addition due to Postnikov is here is that he makes the connection to toric geometry, and in particular this is relevant for our work here. So he is interested in computing volumes and counting lattice points, and this is where these formula come from, and this is what it makes it useful for this application to economics that we have in mind. All right, and so the story doesn't end here. Again, there's the connection to the talk by Cynthia Vincent. So there's recent work by Brendan and her related to combinatorial Hodge theory, and so these Lorentzian polynomials. They also make an appearance for these symbodies and our analysis, but they so this is beyond the scope of this talk here. But let me just say, so this is just the natural extension of all this work on polymatroids and this optimizing submodular functions that was mentioned before. So in more algebraic terms, so the frontier currently is studying Lorentzian polynomials. Right. Okay, so I have about 2 minutes, I guess, and so I didn't explain what this SGA auction, the straitjacket auction, actually is, right? So, and let me use the 2 minutes, the final 2 minutes, to do exactly this, and I tell you how they can be computed. So the main consequence of all the theory that I told you is that I can express the volume of this symbody now, which depends on these parameters alpha 1 up to alpha n, as a homogeneous polynomial in the parameters. And this is a homogeneous polynomial of degree k, yes. So I have n prices. So in general, I will be interested in the case where k is the same as n, but it makes sense to keep these two parameters separate because I have several polynomials to consider. And now I can define the prices. So for me, an auction is just, so the only thing that the seller needs to do is to decide on the prices for the bundles. And the bundles only depend on their sizes. So for each size, I need to say how much it costs to buy those many items. And so the auction is just a point in R to the n, right? It's just P1 to Pn. And I explain this as a solution to a system of polynomial equations plus something. And so these polynomial equations are exactly these. So these volume polynomials, so that come out of this toric geometry, if you wish, and Lorenz's algorithm. And so I plug in the price differences. Now, the prices are the unknowns. I want to find solutions for these polynomial systems in the P's, and I need to do the substitution that I explained before. So these alphas are differences of subsequent prices, and so the volume needs to satisfy a certain constant. And now, so in order to actually define a submodular auction of the kind that we are studying, I need to have to impose the extra condition, namely exactly the submodular condition for the prices. This is this here, and the non-negativity. And so for technical reasons, the easiest way to spell it out is to adopt the convention that P0 is 0. So this is necessary in order to make sure that the buyer doesn't need to pay anything if she doesn't get anything. And the other technical assumption is that P minus 1 is -1. So then everything works. And so the thing is, if you have the system of polynomial equations, and then you are looking for solutions which satisfy these conditions. Of course, this is a real polynomial, and you need to make sure you're only interested in real solutions. And a priori, it is not obvious that these solutions exist. So these polynomials and this system of equations already occurs in Giannakopoulos and Koutsoupias. But our contribution is that under these conditions that I explained to you before, these systems do have a solution. So this is what we actually prove. And we prove something more general. Okay, so this is, now you know how these things work. And here's one example for n equals 3, like the first non-trivial case. So this is how these systems look like. The polynomials become increasingly messy, the degrees increase. And so here we have a unique solution which satisfies the submodular conditions. And this is how it looks like. The first one is a rational number, and then these two others are algebraic numbers. And so then we just give approximate solutions, but we are able to, so with the computation, with standard computer algebra methods, this is my final slide, we are able to get at certified prices. So we can prove these are provably correct within a certain range. So we, for instance, in the paper, so there's a table. And so there the prices are spelled out up to 53 bits precision, and this amounts to 15 digits after the period, 15 decimal digits. Okay, and so the software that we're using is Polymake, our own software for polyhedral computation, and homotopy continuation software by Paul Breiding and Sascha Timme. For solving systems of polynomial equations. And so Sascha was a joint PhD student of Bernd Stomfeld and myself. And I'm at the end of my talk, and so the obvious conjecture which remains is that this straitjacket auction that I briefly sketched is optimal for symmetric and submodular prices, even without the technical non-degenericity conditions that I didn't explain much. And actually, it should even be true in the non-deterministic setting, but for the non-deterministic case, I don't have any idea how this should work currently. This is what I wanted to share, and thank you for your attention.